So I'm switching on the screen when we're talking.
Gunnar, can you hear us? Gunnar, can you hear us?
Oh, yes, I hear you fine.
All right, okay. Can hear you too. So if that's okay, Sada will be chairing the session. So I'll go and chairing the session. Right. Okay. Okay. All right, so it's a great pleasure to introduce Gunnar Carlson, who will be our first speaker this afternoon, and who will talk about computation, duality, and motion planning. Great welcome to Gunnar.
Okay. Thank you very much. Thank you, Pavel, and everyone for the invitation. I'm really glad this meeting is happening, and looking forward to telling you about some of the things I've been thinking about. Oh, hang on. There we go. So motion planning, you know, this picture kind of shows what it's about. I think, you know, one starts out at an initial point. One wants to navigate a domain where there are lots of obstacles, and you get through to a goal at the end. Now, so that's one aspect of it. A slightly different one is when you think about sensor nets. It's the same problem essentially, but now in this case, the obstacles are collections of balls. They're not really obstacles, they're sensors, and you're trying to avoid being sensed. Sometimes those things could be moving as well. So there's a large class of problems here. And I want to talk about how to address them mathematically or with topological methods. So first step here is to formulate the problem mathematically. Let's think about a domain in Rn, and suppose that we have a region C inside that domain, what C for covered region, and X and X prime in the domain minus C. So we've got 2 points that are avoiding that covered region, and we're interested in studying the set of paths in D minus C going from X to X prime. And we might be wanting to do that in a dynamical setting where the obstacles are moving as well, and we have to create a moving path that avoids the the covered region. Now, but just why would we want to study the set of paths, or the set of actually homotopy classes of paths from X to X prime? Here's one motivation. Ideally, we'd like to optimize for some kind of minimal path length, or minimizing a notion of energy of the path. And so here we'd want to study the different classes of paths and in each one we might want to try to optimize within that homotopy class. So here you have the homotopy. The red parts are obviously the covered region, and you can see here that we've got different possibilities. Now, the thing is that what we wouldn't want to do, we wouldn't want to try to apply a lot of the standard optimization algorithms to this situation directly, because and those would include kind of gradient descent methods, and we wouldn't want to do that because, well, there's a standard problem that one has with those. Depending on your starting point, you're going to come to different endpoints, and in this case, that kind of can potentially happen in spades. So the homotopy classes of paths correspond to different basins of attraction, if you like, corresponding to different local minima. So the hardest problem in optimization is the presence of too many local minima. But the homotopy classification of paths is really quite a useful pre-processing step, because once you have a homotopy class, you can optimize within it. So you assume that each homotopy class of paths corresponds to some kind of basin of attraction, and you carry out the optimization in there. This is kind of parallel to a lot of work, or reflected in a lot of work that's been done on the pure math side. For example, one often studies, the shortest loop inside a homotopy class of loops within a manifold, or even homotopy classes of, say, maps of a two-sphere in, has been studied by Sachs and Uhlenbeck and others. So the question becomes, we're going to want to study the topology of complements. So suppose that we have an embedding of topological spaces y contained in X. We have topological information about X and Y. What can be said about the topology of X minus Y? In particular, can we recover topological invariants of X minus Y, such as homology, cohomology, homotopy, and in particular, path components? Now, the question is, why should this even be possible? What should the relationship be? Well, the first results, and the only results that we're going to talk about, say that we can obtain homology in the case where the ambient space X is a manifold. So, and that's the Alexander duality theorem, which I suspect people are familiar with. So let me summarize it for you. So Y is contained in a manifold X, and Y is compact. And in the case of Rn, we have this kind of statement here where the reduced homology of Rn minus Y is isomorphic to H upper n minus I minus 1 of Y. And similarly in Sn, which is the kind of the cleanest statement, you can see here it's an isomorphism between the reduced homology and the reduced cohomology on the other side. And for a general manifold, though, the statement is that there's a relative homology calculation. Hi of X and X minus Y is isomorphic to Hn minus I of Y. You notice here, this is not a direct statement about X minus Y, but one assumes that one knows Hi of X. And so the Hi of X, X minus Y, when related with an exact sequence, can get you at the homology of X minus Y. Okay, so now here's a question then. So, all right, fine. So we've recovered the homology or cohomology of the complements, but it's kind of a long step from there to being able to optimize within, within any path space and so on. We probably need to know the actual space. We need to recover the actual space from Y. So, and let me talk about, there's a nice step one can take in that direction called Spanier-Whitehead duality. It says, if a compact Y is embedded in Sn, you can consider the complement of Y in Sn plus 1 also contained in Sn. So, and what you find then is that Sn plus 1 minus Y is isomorphic, is homotopy equivalent to, in fact, homeomorphic to, I think, the suspension of Sn minus Y. So what you really have here is that X and Y are said to be stable homotopy equivalent if two suspensions of them are homotopy equivalent. And so the space therefore determines a stable homotopy type. And in this case, what we're saying is that Y determines not only the homology of the complement of Y for an inclusion, but in fact, it determines the stable homotopy type of that complement because of this statement about the suspensions up above. And the key fact that's important, the reason this turns out to be true is the fact that for large n, all embeddings of Y in Sn are isotopic. So the thing is this, that if I have a space Y sitting inside Sn, I can't say, just from the knowledge of the space, what the complement is. In fact, it's dependent on how the space n is embedded inside Sn. But for large enough n, the two embeddings are isotopic. And when two embeddings are isotopic, you get the same complement. The complements are identical or homeomorphic. Okay, so now the question is, but you know, we don't really care about that stable world. We don't live in that stable world. So we really want to know the actual spaces involved. And so the question is, for fixed dimensions, is there actually a dependence on the embedding? And the answer is clearly yes. And we know some very nice examples of that, because knot theory tells us that the circle can be embedded in many different ways in R3. And in fact, knot theory is all about parametrizing those embeddings or trying to understand or to discriminate between such embeddings. In this case, the stable homotopy type is always, you know, the sphere. So here, the stable homotopy type of the complement, of the knot complement, is always a sphere. But in the actual dimension in question here, when you have an embedding of the circle in R3, it's not. So the fundamental, so the knot complement turns out to be a key invariant of the knot. So when you compute pi1 of this complement, they're often very complicated, very interesting fundamental groups that occur. Now, of course, once I suspend it, once I embed it inside R4 or R4, that difference goes away, that fundamental group goes away, and I'm just getting left with something which is a two-sphere in that case. And I might even have embeddings of disjoint unions of circles. You know, in this case, these are called links. Okay, so homology or cohomology by itself cannot detect the difference between these homotopy types of complements by the Alexander duality theorem. But fundamental groups definitely do, right? So fundamental groups can, as they do in the case of knot complements, it's the primary invariant there. But let me say, but you know, computationally, yeah, more power to people who study knot complements. It's not suited for sort of TDA or computational topology methods, certainly at the moment, because the whole group theory is probably not so computational. But there are other situations. So there are simpler situations where the same phenomenon occurs. In other words, where you have two complements that are different, but that when you suspend them, they become equivalent. So let's look at these two. Let's look at the torus on the left, and look at the on the right. You have a space which is a bouquet of a sphere. That green thing is supposed to be a two-sphere, and then I have two circles, and they're all pinched together at the same base point. Now we look at those and we say, well, those aren't the same. On the other hand, we compute homology, and we find that as groups or vector spaces, they are in fact they produce isomorphic things, because they both produce, you know, a single Betty naught, Betty 1 equals 2, and Betty 2 equals 1. So how do we distinguish these things topologically? Clearly, from my statement here, just homology alone won't do the job. Okay, so let me remind you now about some technical statements about homology and cohomology. So the Künneth formula, for example, describes homology and cohomology of products x cross y. And for simplicity, we'll take the field coefficient case here, where hn of x cross y is the direct sum of the tensor products of hn minus I of x and hi of y. So that's a very clean, explicit formula for the homology of a product. And the same thing holds true for cohomology. So, and we'll talk about, we'll say that the more compact description is as graded vector spaces here, right? So, you know, where you take two vector spaces, two graded vector spaces, you tensor them together, and the component in degree n is the sum of vi tensor wj, where I plus j equals n. Okay. Now, so again, for the torus, this is our statement here. So the cup product is a homomorphism like this of graded vector spaces. It's given by a composite. So it's first of all, you have got the Künneth map, the Künneth isomorphism, H star of X tensor H star of X into H star of X cross X. But then critically, you use the diagonal map, which is the key thing here, the functoriality or the contrafunctoriality of cohomology tells you that if I have a map of spaces, I have an induced map on cohomology. So I've got the Künneth isomorphism followed by that diagonal map. And so the image of X tensor X prime in here is denoted by X cup X prime. And it turns the cohomology of X into a graded K algebra. So it becomes a ring now instead of just a graded vector space. So that's additional structure, very, very useful. And a very interesting fact or useful fact here is that for XA suspension and X prime, and let's say it's, and X and X prime are positive degree elements in H cohomology of X, X cup X prime equals 0. So in other words, for suspensions, these cup products all go away. But they don't, for example, for the torus, they don't, because, and we'll see that in a second, but this means that cup products can detect the difference between unstable homotopy types that are the same as stable homotopy types. So the torus gives an example because the graded ring cohomology of T is isomorphic to a Grassmann algebra here. So a Grassmann algebra means that, X times Y is non-zero, and X times Y is minus YX. But of course the squares, the cup product squares are still 0. So notice this is quite different from the suspension case where you could not have X cup Y equals it being non-zero. So T, that tells us T is not a suspension, and in particular this bouquet here could not be the same as T because its cup products are all trivial. So and the reason B is a suspension is that the space that it's a suspension of is the circle disjoint union with 2 points. So it follows that the cup products of positive elements vanish, and the homology and cohomology of B and T are still isomorphic as vector spaces. So, and it turns out that one can show that the suspension of T is actually homotopy equivalent to the suspension of B. So in other words, these homotopy types definitely become the same after a single suspension. Okay. Now, so let's see. So how are we going to use cup products in the problems that I'm interested in? We've used the cup products here to distinguish between two unstable homotopy types. That's great. But now I want to understand how to use it in this kind of motion planning kind of situation. So H naught X is a vector space with dimension equal to the number of path components of X. That's well known, first calculation that you do with homology. And so, but the path components determine a basis for the vector space H naught of X, because each one corresponds to an element in H naught. So there are some elements in H naught of X which are not which are not a part of that basis, right? Obviously, and so they're instead linear combinations of components. And homology alone, by its calculation, and the duality theorems do not permit us to identify the basis. So in the statement that what we'll say that in the in the homotopy theoretic language is that H naught does not determine pi naught as a set valued functor. Okay, so how can we get at the set valued functor? Well, H naught of X is a ring under cup product. So H naught of X is isomorphic to the K algebra of K valued functions on pi naught of X under pointwise addition and multiplication. Now it turns out, therefore, that the set of K algebra isomorphisms H naught of X to K is in one-to-one correspondence with the elements of pi naught of K. This means that we can recover pi naught from the K algebra valued functor H naught of X, H naught, so H upper 0. So while we could not we could not get at the components just from the vector space structure, we can get at pi naught if I include the cup products computed on H0. And okay, so now the various duality theorems allow us to understand the homology of the complements, including H naught. can we use those same methods? Can we use those duality methods to recover cup products of the complement and consequently the set pi naught applied to the complement? And it can be done, and it uses the fact that cup products are induced by a map, namely the diagonal map, and a functoriality results for the duality theorems. So let's look here. So the Alexander duality isomorphism for x equals Sn described above is functorial. So in the sense that you have this kind of inclusion here of y naught contained in y1, you have this this diagram like this. So notice that the map on the right is induced by a map of spaces, and then so is the map on the left. And the map on the left comes from the fact that you see it goes from let's see, why not? Because they are smaller. So x minus y1 is contained inside x minus y naught. And so therefore I get a map, the cohomology map going in the opposite direction. The horizontal maps, are the duality isomorphisms. And so this is a key statement here. This is a functoriality for the computation of Alexander-Whitehead, Alexander duality. Okay, so now we suppose we're given a compact set. We let the complement of A equals Rn minus A. So again, HI reduced of complement of A is Hn minus I minus 1 of A by the Alexander duality theorem. So we'll let the complement sub delta of A denote the complement of A inside A cross A within R2n, R to the 2n. So what we're going to be studying here is we want to understand the effect of the diagonal map. And so I will have this compact subset. It's contained inside R, the diagonal Rn within R2n. And so I'm going to study that complement there. We'll also let C of A cross A denote the complement of A cross A in R2n. So there's an analysis of both of these that one can do. So remember now, H upper 0 of A cross A is therefore isomorphic to H2n minus 1 reduced of the complement of A cross A, and H upper 0 of A gives you H2n minus 1 reduced of this diagonal complement. So what we obtain then is a map from the complement of A cross A into the complement sub delta, the diagonal complement, inducing the cup product on H naught of A via functoriality of Alexander duality. So let me say here, we're going to get a map from H2n minus 1 of these gadgets, H lower 2n minus 1. And when I translate by Alexander duality, that's going to get me to the cup product on H naught of A, because this is the dual to the diagonal map. Okay, so now there's a question: how do we use this dual description of cup products computationally? I mean, after all, this is kind of this is an abstraction here, duality abstraction. So we're going to try to understand how to do this computationally. And so how might I do this? I mean, the question already, when you're talking about computational topology, the question is, how is your space represented? If it's represented just as points or then it might be very difficult to get at it computationally. And so we have to assume beforehand some some description which gives rise to something which is computationally addressable. And so what we're going to assume is that the covered region is given as a union of convex regions, as one might have in the case of a computer-aided design description. Okay, so we think of that as a small number of convex sets. And the thing is this, that when it's given in that form, since the sets are convex, it means that all the intersections are empty or convex themselves and therefore contractible. And so the nerve theorem provides a compression of the calculation of the homology of C. In other words, my covered region, of course, is just a set of points, an infinite set of points, which I could think about computing in the abstract way. But on the other hand, that's not so useful to us. But what this says is that we can compress that calculation into something where the chains are just, the sets that we've got in the covering, there are overlaps between, collections of them. So the question is, so that's a nice description of the homology of C made computational. So the question is, are there analogous coverings of these complement of A cross A and the complement of sub delta of A, so that these inclusions respect the coverings? Yeah, this is joint work with my collaborator Brad Nelson. So we suppose that C of A is covered by convex sets U alpha. So let me say C of A here is the uncovered region, and so C of A is the covered region. That's the complement, if you like, of the uncovered region. So I'm assuming that that's covered by these convex sets, and then C of A cross A is covered by U alpha cross Rn, union Rn cross U alpha. Let me see here. Let me remind you that, so the complement of A cross A, let's think about that for a minute. The complement of A cross A is a union of two pieces. It's a union of complement of A cross Rn. So in other words, complement of A says I'm not in A in the first coordinate, or I'm not in the complement of A in the second coordinate. And so that says that I'm covered by U alpha cross Rn, union Rn cross U alpha. And so what that says is that it's roughly the same size as C of A cross C of A, and we'll call this covering U join, because this actually exhibits the complement of A cross A as a join of C of A cross C of A with itself. How about covering C delta of A? We'll recoordinatize Rn cross Rn via this formula right here. And delta is now embedded in the first coordinate, with the second coordinate identically 0, because the diagonal, when I have the diagonal embedding of C of A inside Rn cross Rn, that will become 0 when in that second coordinate, when we take the W minus V. And now here's the interesting thing. We need to cover Rn minus 0. So that's that second coordinate by n+1 cones with the origin removed. So a kind of a picture like this. So the reason that I need to do that, well I need a covering by convex sets of Rn minus the origin, right? It's because I have on my right-hand factor is Rn, but with the origin removed, because I'm computing the complement there. And so I'm covering this by the n+1 cones V naught through Vn with origin removed. So I'll let V equal V naught through Vn. And also include the sets U alpha cross minus epsilon and epsilon in the modified coordinatization. So this set is now a covering of C delta of A by convex sets. So we'll now form a covering of C of A cross A by forming all possible intersections of sets U from the original covering of C of A cross A with this W cross C of A cross A, where U is in U join and W is in W. The reason I'm doing that is I want to make sure that the inclusion of C of A cross A into C sub delta of A is in fact preserves coverings. That is to say, has the property that every set within this U modified covering is contained inside one of the sets of the covering for C delta of A. So I've had to grow my covering a bit, but nevertheless the size of it is not too big. And at this point now I've got a map that's actually realizing the dual to this product map, and it's a map of simplicial complexes. So what we will do now is we'll work under the assumption that we can compute the cohomology with products of the complement of covered regions. By the way, let me say that, come back here to this, choosing this covering of the, the second copy of Rn minus the origin. That is the thing that's really that captures part of the embedding. In other words, that thing can differ depending on the choice of embeddings, and so that's kind of what's what encodes that property here, or encodes the embedding. Okay. All right, so let's think about motion planning for a minute. Let's C denote a covered region in Rn. Let x and x prime be 2 points in Rn minus C. We'd like to determine the set of homotopy classes of paths from x to x prime staying in Rn minus C. So we suppose there's a covering of Rn by convex sets, U alpha, so that the intersections here, U alpha 1 intersect U alpha I, intersect Rn minus C, all have homology vanishing in dimensions less than or equal to 2 and are simply connected. So what this means is that we might have a covering of Rn so that these intersections of the of the covered region behave like discrete sets of points. So then we'll be able to compute the above mentioned homotopy classes of paths, because what we will have is we will have the complement broken up into into discrete pieces, which have no higher homology, and because I've got the cup products, I can actually understand the relationship between those sets of components. Now, so one thing that we might consider, we might have a motion planning problem or a situation in which we have moving sensors. So in this case, what we want to do is we want to have a path in the ambient space which avoids the obstacles at every point in time. So we'll formulate the problem in terms of spaces over a base. So the ambient space will now be x cross the interval 0, 1 cross Rn, consisting of a position and a time. So pi from x down to 0, 1 is the projection. And so the time-varying obstacles will now consist of a subspace y contained in x, which itself then has a projection down to 0, 1. So, and by an admissible path will mean a section like this. So a map sigma from 0, 1 to x minus y. So this means a continuous map from the interval 0, 1 to y, so that pi composed with sigma equals the identity on 0, 1. So many questions can be asked about such sections. Does one exist, for example, is something that one could ask. And how many homotopy classes are there? And what is the structure of the space of sections in general? So, how many homotopy classes are there? Well, that kind of says what is the set of components of the space of sections. So there's a lot of work done on the first problem by, that is to say, do they or do they not exist, by Grist and De Silva, by Henry Adams and myself, Grist Krishnan, and also Michael Vedemo Johansson has done interesting work in this direction. And I believe the second and third problems are not addressed, although in Michael's work, I believe they are also addressed. So now the second and third problems are potentially useful as starting points for finding optimal paths. So here I could ask them to try to find some kind of optimal evasion path, if you like. So the sections here of that uncovered region would be called evasion paths. The second and third problems would be potentially useful as a starting point for finding optimal such sections under some notion of optimality. So this is joint work with Ben Filipenko and Wyatt Mackey. So we'll break up 0, 1 into closed intervals that intersect in the endpoints only. Okay, so let's think of that. So so we'll construct the spaces pi inverse of is and pi inverse of is intersect is plus 1, and we'll create a zigzag diagram of spaces. So remember, a zigzag diagram is like a persistence diagram, but with alternating arrows going either to the right or to the left as it alternates. Now, what is clear is that if there is a section, then the zigzag barcode will have a long bar. But the converse is not true. Okay, so let's see. Okay, so, oh, hang on. So let's look at this. Let's look at this example. And so here, let's look at the upper example. So you can see here that we've got a dark region, a covered region, covered in which is black, and where you can see that there is in fact an evasion path, because as I move, let me use. So here we go. I move from this open region. I move in here. Now this little part opens here, and so I can move my as an evader. I can move between the two prongs coming out, and then I can put myself inside this loop, open it up at the bottom, and obtain an evasion path. So what that tells you then is that that there's a path, as you can see. In this one, I can start here, I can continue here, but now I've got no place to go. I'll still stay at the top, and ultimately I don't have an evasion path. Now, the interesting thing to notice here is that, in fact, the covered region is topologically equivalent, homotopy equivalent as a parametrized space to, in both cases, I should say. The question is all about an embedding. So this is about two distinct knots in this situation. And what you'll notice is that the embedding has the property that these prongs go downward here, and the loop goes downward instead. And so these are two distinct embeddings. And so, and they're captured by the fact that in these pictures here, we will see that there's no evasion path. On the other hand, the zigzag persistent homology is actually is the same, because of the fact that there is a duality theorem for this kind of zigzag persistent homology, or so-called parametrized homology. And so so the duality theorem tells you that there's that the homology alone would tell you that there would suggest that there is an evasion path. Okay, sorry. So now the methods that we get from above, allow us to obtain a zigzag of cohomology algebras. Okay. So we've got actually the cup products of the cohomology algebras. In particular, for that, I can compute the H0 of the uncovered region. So what this means is that we can obtain a zigzag diagram of sets, which is a pi naught of pi inverse of is and pi naught of pi inverse of is intersect is plus 1. So instead of having just a zigzag diagram of vector spaces, I now have a zigzag diagram of sets that describes the components of the uncovered region at every point here. So, and it turns out that this zigzag diagram of sets answers exactly whether there is a section or not. The vector spaces do not, but the sets do. And the way that that works is a zigzag diagram of sets will produce a directed graph, if you like. So imagine that we have the set of components over every interval, and then over the intersection of the pairs of intervals. And whenever there's a relationship between one of those components, when it maps from the one to the other, I will draw an edge. And so what I get is the zigzag diagram of sets gives me a graph with a map, or a projection map, over the real line or over an interval. And so when I have that graph, I can exactly enumerate all the all the sections of that graph, and that's purely a combinatorial calculation. So now, interesting thing is that it also gives a great deal of information about the space of sections. So it gives complete information about the connected components of this, the space of sections from the zigzag of sets, together with the zigzag information from the fundamental groupoids. So let me step back for a second. One might hope that this graph that we described here, where we compute the connected components, one might hope that it simply is the the space of or the connected components of the space of sections. They say the space of sections of that graph is, and indeed there is a surjection from the components of the space of sections down to this to the sections of this graph. So that's surjective. On the other hand, it turns out that it's not necessarily an isomorphism or a bijection, because let's imagine the following situation. Let's suppose that our space is actually a circle, so just actually a fibration or the product projection of the circle cross I down to I. And I ask about the space of sections of that thing. Well, so of course, I can get a section that stays at the base point, but I could also get a section that starts at the base point of the circle and then rotates around one time before ending up at that base point at the end of the interval. So what that tells me is that there is some effect of fundamental group going on inside here that needs to be incorporated. So what we've done, Wyatt Mackey and Ben Filipenko and I've done, is described it exactly in very familiar terms using pi naught and pi 1. So there's something very analogous to the so-called lim 1 calculation that one does in algebraic topology to compute the homotopy groups of towers of fibrations. So there's a very simple description in terms of exactly the fundamental groupoids, and the fundamental groupoids are things that don't require choice of base point. I keep track of base points and the space of paths between base points. So if I understood completely the fundamental group of all the elements and then the effect of those maps, then I could compute the space of sections, or the components of the space of sections. Okay. Now, 2 points here. So that might be discouraging, because of course fundamental groups are very hard to deal with computationally. On the other hand, in the case of most of these applied problems, we don't really expect that to have an effect. We don't expect that to worry us too much from the point of view of the optimization problems. Because if you think about trying to consider that circle case again, if I choose, one section by some method, so I might, for example, just select, base points within each of the components that describe nodes of the graph in question, and sort of choose paths there, and perhaps those spaces are rather that it's simple to describe a path within each of the fibers. Then I don't expect that I will ever get to one of these sections which loops around many times. I sort of expect that when I sample or choose there, I'm going to get to one of the simpler paths. And so therefore we kind of we believe that the relevant information for getting at the optimization problems is most likely coming from exactly that graph of components, and not involving the fundamental group stuff. Now, a second point, coming back to the original, motion planning situation, there one might very well want to understand higher dimensional cohomology, in particular H upper 1 and H upper 2. And the reason for this is that there's a machine called the unstable atom spectral sequence, which is designed to get at the cohomology of spaces of paths, and from using only information about H0, H1, and H2. The unfortunate aspect of it is that it will only capture completed information about the fundamental group. So, the atom spectral sequence can never get at a complicated fundamental group. But if the fundamental group is abelian, for example, or even nilpotent, you can get at it. And so I think it's reasonable to assume, again, that those complicated fundamental groups won't appear so much in practice. And so, a hope then is that one should attempt to build that unstable atom spectral sequence, which is needed only in low degrees to get at this component calculation. Okay, and I see that I've kind of I've underestimated on time here. I'm actually kind of finished with the talk here. So I thank you for your attention, and I'm happy to answer any questions.
Thank you, Dennis. Any questions? When you subdivide the intervals, where do you stop? I mean,
Where's the condition? Yeah. So look, what I think is that first of all, ultimately this answer should be in terms of parameterized homology and cohomology, but of course that may not be readily accessible. So one context in which we stop the subdivision is we consider the situation where the projection map down to the real line is a Morse function. And for the boundary of the covered region, and so in that situation, we would really we want to make sure that the intervals are such that no interval contains in its interior a critical value, and if you do that, then you're in good shape.
Right.
But we've formulated some other conditions as well.
So this is work in progress, I guess, right?
Sure. Well, the work is definitely work in progress. In particular, the computational aspects of the cup products. The fact that we can compute the cup products of the complements. In some examples where we have a CAD description, a computer-aided design description of the the covered region. That's definitely work in progress. Some of the others is completed now. This description of the set of components of the space of sections, that is completed. I mean, we're revising the manuscript and so on, but that is done. And so we can then show that we can get at at least this graph of components. We can show that we can get at that. And of course, the analysis of the fundamental group is, from the computational point of view, is still problematic. Yeah.
All right, there's a question here.
So you mentioned along the way that the cup product restricted to degree 0 cohomology is a K algebra on its own. Is there some nice simple intuition to what the cup product is doing in that case?
I'm sorry, is the question, is there a generalization to computing the cup products in higher dimensions?
No, is there an intuition for the cup products in degree 0?
Oh yeah. How to say this? Let's see. You might consider it kind of dual to the homology situation, where one has a co-algebra. And so now if you look at the components, you'll see that the components have the property that they're kind of group-like there. They go to, a component X goes to the X tensor X. And so that's called group-like in the theory of Hopf algebras. And so, that's kind of the intuition. Anything which is not, a sum of things. So for example, if I have x plus y being x and y being components, x plus y goes to x plus y, goes to x tensor x plus y tensor y. And so it's not group-like in the sense that it's not equal to x plus y tensor x plus y. So the intuition is kind of algebraic. It says that on the on the cohomology side, the algebra is a semi-simple algebra. It's actually a product of copies of the ground field, as we saw. It's the functions on the set of components, and so there are the idempotents. In fact, the simplest idempotents are the points that the functions on a single component there. And so when I add them together, I get the entire algebra, but the product between them is 0. So that's how it's captured algebraically, the fact that this is an algebra with a lot of 0 products in it.
Thank you.
All right. I think this is all the questions we got.
Okay.
Thank you again very much, Gunnar.
Okay, very good. Thank you very much.
Yes, and thank you again for joining us so early.
All right, thank you. Best wishes for the conference.
Thank you so much. So we'll have a coffee break right now, and we'll start again with contributed talk session in 40 minutes. Remember, in the session which is happening in the room which is closer to here, the talks are actually reversed. That's it. Thank you, Gunnar. Thanks, everybody, and see you in 40 minutes.
Substitute.